Suppose that I would like to find the area of a general surface, such as the one pictured below, R of uv. One way I could go about this is to subdivide this surface into smaller regions. So maybe I could draw contours along this surface where maybe, say, u is constant. And then I could draw contours along the surface maybe where v is constant. And then hopefully, as you see these regions getting subdivided, you can see that each smaller patch looks like a parallelogram. And so maybe we could approximate the area of the surface on this small patch by finding the area of the parallelogram that approximates that area. In order to do that, I'm going to need to define these two vectors. This first vector, okay, is a tangent vector, say r sub u. And then this second vector here, that's a tangent vector, r sub v. And so what I'm going to do is I'm going to define those two tangent vectors at a particular point. So I'm going to let r sub u, okay, be the tangent vector at a particular point. We'll call that point u sub I v sub j. And r sub v is going to be the other tangent vector at u sub I v sub j. Okay, so then what I want to do is I want to approximate the area of that is shaded currently in purple. So I want to approximate, say, that area. I'm going to call that area S sub I j for the area, or I'm going to call that region S sub I j. That's going to be a small piece. And the area of that region and the area of that small piece, S sub ij, is going to be approximately the area of the parallelogram formed by the two vectors r sub u and r sub v. So it's going to be approximately the area formed by those two vectors. But the area formed by those two vectors is the cross product of those two vectors. So it's going to be approximately r sub u cross r sub v. But those vectors need to be scaled so they're the right size. So I'm going to scale r sub u by delta u and r sub v by delta v. And so the approximate area of that little piece of surface is the area of the parallelogram r sub u cross r sub v times delta u delta v. So here on the diagram, if the parallelogram is that small, then those two vectors are actually r sub u delta u, and then r sub v delta v. Okay, so now I've found the area of one piece of the surface S sub ij. And now I can sum over all the possible pieces to find the area of that surface. So the total area is going to be approximately the sum over I and the sum over j. We're going to sum over all the little pieces. So that's going to be the sum over I, sum over j of Ru cross Rv delta U delta V. And we're thinking about Ru and Rv as being indexed by I and j, as I've shown above. Okay, well, that's an approximation of the area. What I could do to make a better approximation is I could let delta U and delta V be smaller, so I could consider more subdivisions of this surface. As I increase the number of subdivisions of the surface, then the regions that I'm finding the area of are going to be closer and closer to the areas of these parallelograms. And so I'm going to get closer and closer to the true area of the surface. So what I'll want to do is then take a limit as delta U and delta V go to 0. Okay. And if I do that, if I take a limit as delta U and delta V go to 0, then I can find that this Riemann sum, in fact, becomes the actual, or becomes an integral that represents the exact surface area. Okay, so I'm going to define the area of the surface using a double integral. So it's going to be a double integral over some region R that U and V live in. And then I want to find the magnitude of Ru cross Rv. Okay, well, Ru cross Rv, remember, that's actually the normal vector. So I should draw in this normal vector. So we'll call that n sub ij for the normal vector. Okay, so we're going to think about Ru cross Rv as being there the magnitude of the normal vector, n sub ij. And so our double integral is going to be a double integral over the magnitude of the normal vector, depending on u and v, du dv. Another way to write that is a double integral over the region R that u and v live in of Ru cross Rv du dv. And so now we've defined an integral that will give us the area of a parametric surface. So let's move on to an example so we can see how this process works. So our example is to find the surface area of a sphere of radius a. So You might recall that a sphere of radius a has surface area 4 pi a squared. But you might ask yourself, where does that formula come from? How do we know that that's the surface area of a sphere? Well, we can use this technique. We can parameterize the sphere using two parameters, theta and phi. So a sphere of radius a is going to be, x is going to be a cosine theta sine phi, and then a sine theta sine phi for y, and then z is going to be a cosine phi. So that is our parameterization of the sphere. And then what we want to do is we want to apply our surface area double integral to find the area of that sphere. So what I'm going to have to do is I'm going to have to find the two tangent vectors to the surface. I'm going to need the derivative of r with respect to theta. Okay, so that's going to be minus a sine theta sine phi, then a cosine theta cosine phi, sine phi. And then the derivative of the last component with respect to theta is actually going to be 0. And then phi, the derivative of r with respect to phi is going to be a cosine theta cosine phi, a sine theta cosine phi, a cosine theta cosine phi, that's the correct. Then a sine theta cosine phi, and then minus a sine phi, taking derivatives with respect to phi. So that gives us our two tangent vectors, but then what we want to do is integrate the magnitude of the normal vector. Okay, so I need to find the magnitude of the normal vector. So first I have to find the normal vectors. So the normal vector is going to be r theta cross r phi. So that's going to be I, j, k, and then minus a sine theta sine phi, and then a cosine theta sine phi, and then 0. And then I'm going to have r phi, which is a cosine theta cosine phi, a sine theta cosine phi, and then minus a sine phi. So I need to find that cross product. I'm not going to go through every detail, but essentially that's going to be minus a squared cosine theta sine squared phi I, and then minus a squared sine theta sine squared phi j, and then minus a squared sine squared or sine phi cosine phi k. So that's the normal vector. Then we want the magnitude of the normal vector. The magnitude of that normal vector will be the square root of the sum of squares of the components. So that's going to be a to the fourth cosine squared theta, and then sine to the fourth phi plus a to the fourth sine squared theta sine to the fourth phi plus a to the fourth sine squared phi cosine squared phi. Now this can be simplified because this cosine squared and that sine squared add up to 1. Okay, so that gives us just a to the fourth sine to the fourth phi. And then you can take a sine squared phi out of those two terms and then the cosine squared phi out of the last term, and that adds up to 1. So ultimately, you end up with the square root of a to the fourth sine squared phi. So now when I find my double integral, okay, I'm going to integrate over all theta, so the integral from 0 to 2 pi, and then the integral over all phi, the integral from 0 to pi, and then I'm going to integrate the square root of a to the fourth sine squared phi, so that's going to be a squared sine phi d phi d theta. Now this is a fairly simple integral to do, and we've actually seen this a few times before, and so when you do this integral, you're going to get 4 pi a squared, which is exactly what we expected for the surface area of a sphere. I do encourage you to go through a few of these computations. Okay, so finding the cross product, r theta cross r phi, and then finding the magnitude of the normal vector. Do those on your own to make sure that you do in fact get that the magnitude of the normal vector is a squared sine phi. And then of course the surface area when you do that double integral is 4 pi a squared.